Okay, terrific. We're all set. So I'm Ben-Sasson from Starkware. I am very sorry that I cannot attend in person, but we have three senior representatives from Starkware who are present at EDCON, and I urge you to take a time to talk to them. So we have Ilya, who's the product lead for StarkNet. If he's in the crowd, he can raise his hand and wave. We have Yoni, who's the engineering lead for StarkNet. If he's around, he can also raise it as a hand and wave. And we have Oded, VP Marketing. If he's around, he can also wave. So please go and talk to them. Frankly, they know stuff better than I do. Ben-Sasson, co-founder and CEO of Starkware. I want to tell you about the next generation of proving that we are very excited about, and this excitement is now shared also by many others in the ecosystem, people at the Ethereum Foundation and elsewhere. So before that, I want to tell you a little bit about what is Starkware about. What are we about? Because, there's a lot of crypto goes through these cycles and there are these ups and downs, and people ask themselves, what is this all about? So I can share with you at least briefly what Starkware is about and where do we come from. So, and with your permission, I'll read it because it's really, really important. This is our DNA. Today, we lack ownership of our digital life. Others custody our assets and interactions. I mean, nation states, large corporations, and they may confiscate our assets with no recourse for us. Starkware challenges this. We envision a world where integrity is publicly demonstrated and is upheld by all. Our mission, which we're working with our team of roughly 200 people and growing, our mission is to create a global integrity web where Bitcoin, Ethereum, and other chains connect and scale so that individuals truly own their lives in a way that cannot be taken and confiscated from them. And we'll achieve this by pushing the frontiers of integrity with math, with code, with open source ZK Stark protocols used in real world applications on a global scale, the top blockchains. That's what we're about. And now I want to tell you about Stwo. Stwo is the world's fastest prover. You should care about this because it reduces the total cost of computation. And you should be excited about this because it's going to hit StarkNet mainnet in roughly half a year or less. And it will hit mainnet of StarkNet without developers needing to do any change in the way they access or interact with StarkNet. So let's take a step back and see where we're coming from. And first of all, let's explain what a validity rollup is. Validity rollups sometimes are also called ZK rollups, but we prefer the more accurate term validity rollups because it's about scaling blockchains using the math of validity proofs. So as you can see on the top, we have the off-chain state, which receives a bunch of transactions. And on the bottom, we have the state on Ethereum. So Ethereum is the ultimate layer of security. And we have, I don't know if you see my cursor hovering over it, but we have the rollup state, which is the hash or the latest state of all the accounts and contracts on the layer 2. And how do we update it? Well, we go off-chain to this layer 2, to the validity rollup, and a bunch of transactions enter the mempool. And then they are sequenced by a sequencer, sequentially, one after the other, and constructed into blocks. And these blocks are, so it's very similar so far to the way the things work on mainnet Ethereum or Bitcoin for that matter. But here's where things are different. On mainnet Ethereum, basically, one entity submits a block and then everyone else in the network has to run through all of the transactions and update the state locally, one transaction after the other to know that everything was done with integrity. But with a validity rollup, we rely on math. So we send these blocks to a prover. The prover is some machine. It doesn't have to be trusted. It doesn't have to be signed. Any machine can be this prover because integrity is actually supported by math and not by authority or reputation. So the prover generates a mathematical proof, a ZK without ZK, that attests to the validity of all of the transactions and to the integrity of the new state. And then a proof is produced, which is sent to a smart contract, the verifier smart contract that sits on layer 1. And only if the verifier smart contracts accept the proof do we change and update the state. And this is a scalability solution, and the reason is very simple. The reason this offers greater scale is that the amount of computation needed to verify a proof is exponentially smaller than the amount of computation needed to run the transactions. What I mean is that if we have, let's say, 1 million transactions taking place on the validity rollup, in order to verify that all 1 million of these transactions happen correctly, the verifier smart contracts need to spend an amount of gas that is equivalent not to 1 million transactions, but to something like, let's say, 100 transactions or maybe 1,000 transactions. So you save a factor of, somewhere between 100 and 10,000 in the amount of computation needed to be done. This is how validity rollups work. Now, here's a brief history of proving, which basically I want to tell you something that I'm very proud of, which is that we pretty much innovated and jump-started a lot of what is today best practice. So the ZK paper and the whole study of proofs and interactive proofs dates back pretty much 40 years to the mid-1980s. And a bunch of people received Turing Awards for it, including this year, 2024. The recipient of the Turing Award is my own PhD advisor, Professor Avi Vigdalson, who also happens to sit on our scientific board. So there's been a lot of research going back 40 years into proofs, where, first of all, I was fortunate to contribute to this in offering the first use of general purpose zero knowledge for privacy, which was Zcash, which I was a co-founder of. And then we had a bunch of mathematical breakthroughs that led to the Stark paper and the underlying protocols such as Fry and Stark. And this was around 2018. And already back then, we said to the world, look, the best way, the end game for scaling blockchains is to use Starks. And we founded a company around it together with Uri Kolodny, a bunch of others. And this was 6 years ago. When we started it, very few people believed that proofs are the way to scale, and even less believed that Starks are a way to scale within proofs. Everyone was talking about, Groth 16 snarks and things based on elliptic curves. But fast forward today, and thanks to the efforts of Starkware, which invented Cairo programming language and the Stone prover and the StarkX scaling system and StarkNet, everyone today agrees that Starks are the end game for scaling. So the ZK sync system, 3-polygon validity rollups, Risk Zero, SP1, they're all based on Starks and our technology. And the reason I'm saying this is because what comes next is going to be even more impressive than what we've done so far. But we've already saved for our customers on the StarkX systems more than $1 billion in gas fees. And we're now supporting roughly 10 teams, 10 separate teams, such as DYDX, Immutable, and Sorare, that are using the StarkX system. Just yesterday, only Immutable, which is just one of these 10 systems running on StarkX, had a TPS of 30, which was among the highest in the L2 world. And we're going to grow even bigger. So we demonstrated to the world that this is the right way to scale blockchains, and Ethereum in particular. And thanks to this, we have a very large and growing ecosystem. Again, I urge you all to reach out to the people from Starkware already sitting among you. Ilya, Yoni, Oded, talk to them. We are the fastest growing L2 over time. and we're staying strong. So where are we heading? What's going to be the next thing in terms of scaling? It is the Stwo prover. Stwo stands for Stark number 2. Our first prover is called Stark number 1. And we think that the third version, which we'll probably start working on, I don't know, in 3 years, will probably be called Strez, for 3 or 3, followed by Squatro, squat. We'll see about that. Anyways, what is it? So first of all, it uses a very, very small field size, which means basically that the basic unit of computation when constructing proofs is not some large number. These are very small numbers that fit inside a word, a computer word. A computer word is 32 bits. So you can fit each one of these numbers inside a computer word, or you can fit them inside a word used by the Bitcoin script virtual machine. It's a very, very small and convenient word size, which is going to lead, as you'll see, to very large speed. We're going to have a much improved virtual machine for Cairo, like, a new version of the CPU that will allow developers even more agility and ergonomic programming. It is based on a beautiful mathematical breakthrough called Circle Stark, and it will use also a bunch of older things that are very good, like the GCAR lookup method and mixed degree traces. And I urge you to talk to our team there if you want to learn more about these fascinating mathematical concepts. So about 2 weeks ago, we measured the amount of computation that you can run. And we broke the world record. We'll probably break it a few more times before we reach production, in the ability to prove a throughput of over 500,000 Poseidon hashes on a quad-core laptop. And you can't see this, but I'm using actually a Mac Pro chipset, and there it's over 700,000, and some people using a Pro Max even managed to prove upwards of 1 million invocations of a hash on a laptop. Now, this is more than 2 orders of magnitude better than anything known previously, at least according to senior people in the Ethereum community. We're pretty much blown away, and we're now discussing with them, whether there are ways to use this to reshape the map for Ethereum, because there's a lot you can do if you have this throughput on commodity hardware. So this allows you to do things like sub-second recursion, which means you can have very fast finality for extremely large batches of blocks. You can have sub-second state diffproofing, which could allow you to even enlarge the state of Ethereum even more. And it opens the door to putting Starknet on Bitcoin, which is something we already declared, that once Opcat, which is the modification to Bitcoin, the soft fork, is adopted, within 6 months we will have Starknet settling safely, not just onto Ethereum, but to Bitcoin as well. And hopefully, after that, to many more chains. That provision, remember, we said that we believe that this integrity web that we're building isn't about just one blockchain, but we must have this sort of web that connects together many, many blockchains so that, people can basically choose and move in a self-custodial way between them easily. And that's our mission, to help that happen. Again, I urge you to go talk to Yoni, Ilya, Oded to learn more about the possibilities opened by Stwo, and also to explore if there are ways to add and contribute to this open source code, whether in the context of Starknet or to do research that can advance Ethereum's roadmap to use it. So let me tell you a little bit about what is, what is the magic, the math magic going underneath it. Again, I won't have a lot of time to explain this. If you are inclined, you can you can Google Circle Stark, and then you can find both a white paper, or you can find a blog that I wrote about it, and Vitalik just released a blog about it. So there's a lot of information and excitement about it. I urge you to read more. So, okay, there's this thing called, there are Merced primes. They are the form 2 to some power -1. And one of the Merced primes is 2 to the power 31 -1. And basically what we're doing is we're going to use math. Stwo uses math that is all about addition and multiplication, where you take remainder, it's called modulo, you take remainder from this specific prime. So you can see that it's enough if you have even 31 bits. With 31 bits, you can represent any number within this world, because we always take remainder from this fixed number, which is why you can fit these two inside the computer words. So you get really great performance. And you also can work with smaller granularity, a little bit like, previous provers used very large fields that had, let's say, 256 bits. And then, but if you want to just represent 1 bit, or, just a word with 8 bits or 16 bits, you were wasting a lot of space because you use these very large number of bits to represent them. But now with the 32-bit, basic element, you have better granularity. It also happens that on hardware, on commodity hardware, such as GPUs and CPUs, the particular kind of computation that is taking remainder from this particular prime is very nice, because 2 to the power 31 equals 1. So basically, if your highest most bit is turned on, you can sort of, turn it off and replace it by the lowest most bit, which is very simple in hardware. So this is why you really want to work with this particular field called M31. However, there's a problem. The problem is that, just as in the case of FFTs, you would really want to have this structure called a mathematical group. And you want the group to be such that it contains, like in a babushka, it contains a subgroup of half the size, which contains another subgroup of half the size, and again and again and again. And for that, you need the group to be of size 2, some integer power, like let's say 2 to the power 30. But the problem is that if you look at M31 and its basic group, the multiplicative group that comes with it, it just doesn't have that structure. It doesn't have the structure of being of the power 2 to the some large integer. So what can you do about this? Well, one solution that already we knew about a few years ago, and this again is another breakthrough coming from Star Wars engineers who are also scientists, and is that once you fix a finite field, there's a pretty large variety of groups you can try to find and work with, and they come in different shapes and sizes. These are, well, they all pretty much come in one shape, the shape of an elliptic curve, but they come in many different sizes. So you could take an elliptic curve and find a group over it and use that group to basically build everything needed for a start, even over the field M31. But this is somewhat expensive and complicated, working with these elliptic curves. Well, the new breakthrough that came from a joint work of Polygon, and also between Polygon and Stark, whereas, scientists, engineers, goes under the name of Circle Stark. You can see the paper is only half a year old or even less. And the idea is to take the circle curve, and take points on the circle and use them in order to find your group that has size 2 to the k. And it just so happens that this works. So in the good old days, the good old Starks that we used previously, you could think that the groups was somehow similar to the group of, basically of integers, 1, -1, 2, 3. So you can think of it as, imagine it somehow as a line. Elliptic curves have this sort of weirder shape, which I'm not going to go into. But now we're actually using a different group, which is the circle. And it is the set of all points, x, y, such that x squared plus y squared equals 1 modulo the prime. So for instance, the point x equals y equals 2 to the 15 happens to be a point on the unit circle over M31, because if you square each one of these x and y's and sum them up together, you will get 2 to the 31, and 2 to the 31 equals 1 if you take remainder from this Mersenne prime. So it turns out that you can find a group over there. Again, please talk to our folks on the ground to learn more. It's fascinating, beautiful math that actually goes back to the stuff you studied in trigonometry and algebra. So it's very, very interesting. Addition or action of the group is like taking, adding angles in some. And why should you care? Well, you get like beautiful new math, which is in collaboration with Polygon Labs, baked into open source code and papers that everyone is invited to read. You get crazy efficient scale, 100x improvement over the current status, and it's open source. Please contribute. And for StarkNet, you will get it automatically. If you write in Cairo and deploy on StarkNet, you will just get much higher scale, much lower cost, the ability to run the proofs and everything on your laptop, lower fees, but you don't need to change everything. You can come already today and onboard and contribute to the open source. So the world's fastest prover, which will reduce computation and will hit mainnet in half a year or so. I want to thank you, and if we have time, I'll be happy to answer a question or two.
All right, ladies and gentlemen, do we have any questions? Yes, okay.
Hi, Eli. I'm Crypto Nerd CM from StarkNet Astro. Nice to meet you. My question is, what is the difference between M31 and Filter 252, and will we use it in Cairo?
You repeat the last part. What is the difference between M31 and
the Filter 252 in Cairo?
252 field, like the stone. What is the difference between the stone field and the Stwo field?
Yes, yeah.
Okay, terrific question. So, as context, right now the proofs are that we generate using the Stone open source prover. Basically use a 252-bit field, and we're going to move to M31, which is a 32-bit field. So the difference, I think, is captured maybe in the simplest way in the cost of multiplication. Stone multiplication, after a lot of optimizations we try to do, even using vectorized machines, is about 40 cycles per multiplication. And Stwo, or M31 multiplication, is 1/3 of a cycle. So it's roughly 120x faster to multiply over M31 than it is over the Stone prime. That is the biggest difference, and that is one of the main reasons we wanted to move over to M31 and Stwo.
Okay, thanks. And I'm a developer on StarkNet, and as a developer using Cairo, should I change it? Or should I need to change the data type, or I just use the Cairo for the M31?
I'm not sure. Its reception is a bit hard. I think you asked if I need to do any changes in Cairo for M31, and the short answer is no, nothing. M31 and Stwo will be applied as is onto all the existing Cairo. I'm not sure if I answered the right question because I didn't hear very well.
Okay, thanks very much.
All right, thank you. We have time for maybe one or two more. Okay, there's another question. Can you come over here, sir?
Hi, Eli. I'm Kevin from Big Layer. I'm very glad to see you on screen, and I'm very proud to have your support and for Big Layer investment. And my question is about the Bitcoin load-ups you mentioned, the Bitcoin prover you mentioned. Because we all know that in Bitcoin UTXO model, we don't have the ability to support the account states of something like Ethereum. And could you share some light or some ideas about how to maintain this state with OPCAT? Thanks.
Yeah. So, okay. The question is, how will StarkNet settle onto Bitcoin, when Bitcoin, first of all, has a very different structure and doesn't have, I mean, its state is captured by UTXO sets, which are constantly changing, and not by something as an Ethereum, an account-based model, and so on. And I agree, it's a very big challenge. But what happens with OpCat at a very high level, and I confess I am not the most technical person to address this, but OpCat basically allows you to concatenate strings and to somehow open and check that certain strings match each other. And this already, and this opens a way in order to do the following. Suppose you somehow had the hash of the previous state, or even the previous state, the hash of this previous state. With concatenation, you can basically open up strings and sort of refer to that state. And you can also use the script language of Bitcoin to actually transition and move this state and update it along, or rather create scripts that can be executed correctly only if they verify the proof and they recognize the previous state, and they will transition the previous state to the new state dictated by the proof. So this is all opened if you have OpCat, and the details of that are extremely complicated. I don't know if Wei-King Chen is in the audience, but maybe again the folks on the ground, if you talk to them, they can explain a little bit more. But it is a non-trivial challenge. However, I will say we're very optimistic that we can solve it. So with OpCat.
Thank you for the answer.
All right, thank you for the question, and thanks, Eli. We're running out of time, so we want to thank you for this session. Let's give a big hand to Eli.
Thank you very much.